millimeter sources.
All right, my name is Wayne Schlingman, and I have done this a follow-up survey to the Bolocam Galactic Plane Survey with my advisor Nancy Shirley and an undergraduate student David Bolin at the University of Arizona, and then the BGPS team, of which many of the members are listed here. So first thing, what is the BGPS? The Bolocam Galactic Plane Survey was basically a galactic plane survey that was done at CSO, which is a 10.4 meter radio telescope on Mauna Kea. Bolocam is a 115 element bolometer. We set out to map the 1.1 millimeter dust continuum emission in the galactic plane at for 120 contiguous square degrees from galactic longitudes of -10 to about 86, and then selected regions in the outer galaxy at galactic latitude ranges from about -0.5 to +0.5 to a depth of about 15 millijanskis. And here's the sample image. Each one of the blue ellipses would be a BGPS source. So what did we do? We did dense gas spectroscopy and heterodyne follow-up on the Heinrich-Hertz submillimeter telescope on Mount Graham. We chose to use the dense gas tracers HCO+ and N2H+ because of their unique chemistry. They have opposite chemistries with respect to CO. HCO+ is formed by CO in the gas phase, and N2H+ is destroyed by it. So N2H+ only shows up when CO has been depleted on the dust grains. They both have similar effective densities to each other, as well as the dust that we're observing with Bolocam. The observations themselves were done using the ALMA Band 6 prototype receiver up on Mount Graham, and our goal was to get sort of a baseline RMS of about 55 millikelvin, and we can do that in less than 2 minutes using that receiver. So we integrated for about 2 minutes using position switching. For every ½ degree in galactic longitude, we went and found our basically an area that was free of all emission by just pointing at that area for 10 minutes to make sure there was no contamination. And once we started observing, we were capable of doing over 15 sources per hour, and we would point and calibrate on available planets about every hour or two. Our source catalog, the BGPS source catalog now contains 8,500 sources, which is, can see here this blue histogram over here. We started observing when that catalog wasn't version 1.0, but we started previous to that. So we had selected out of the version 0.7 catalog 1,400 sources that were supposed to be in sort of equal log flux bins. So our red histogram, which is what we observed, would have been flat if those numbers had stayed the same. But we added to that sample, once we started observing, an additional about 300 sources in L ranges that overlapped with other surveys so we could have complete coverage. So we observed the entire version 0.7 catalog in those L ranges, and then other times when we had just extra time, we would observe sort of whatever was up. And then we also added another 200 sources in the outer galaxy, which you can see over here. On to some of the actual data that we found. So I guess the first thing is our detection statistics. We decided on a flagging scheme of, that basically said that either we have no detection, we have a single line detection, so a nice single Gaussian profile line, where there are multiple detections, multiple velocity components. Did the source have line wings, either blue, red, or both? And did the source show possible self-absorption? So if there was a hint at self-absorption, we'd add it to this category. And we ended up detecting about 75% of those 1,900 sources in HCO+, and about 50% of them in N2H+. In multiple detections, very few sources, and only towards the center of the galaxy did we actually have multiple detections. About 4% of our sources showed line wings, and about 12% actually showed possible self-absorbed profiles. And this is for the entire data set itself. Now, if we go back and look at that deep sample, which was where we were complete in specific galactic longitude ranges, we can see that detection statistics don't change very much. The self-absorption goes down a little bit, and the non-detection rate goes up a little bit, but really we are detecting the same amount of HCO+. What changes over here is the N2H+, just by 10% or so. All right, so there's a lot of data on this plot. Each one of these plots contains 1,800 points, and the contours are basically represent the point density that's below them. So for in blue are the actual detections in this case, and so the blue contours would then represent the number of points that are below that. The red are upper limits. In this case, we're looking at HCO plus integrated intensity on the vertical axis versus the 1.1 millimeter dust flux, or dust emission. And we had, because there was an offset between version 1 and the bird catalog that we were using to initially observe, we went back to the current maps and did photometry with a beam that matched the SMT's 30 arc second beam for every source position where we actually observed it, and that's what's plotted here. And we find that they're fairly well correlated with each other. There's a lot of intrinsic scatter, but these sources are really quite correlated, and the same thing with N2H+. There's a little bit more sources that are over here where there's not quite as much N2H+ emission to pump them up, but they still follow the same approximate slope between these two dense gas tracers and the dust. Looking at the HCO plus integrated intensity versus N2H+, we find the same sort of thing. They're highly correlated with each other, which was not initially expected because N2H+ is destroyed by CO. And so anytime that you have like extremely bright HCO+, you might infer, okay, well, it's probably warm, so the temperature is helping you beef up the emission. But in this case, within our beam, there's still a significant cold gas, a reservoir of cold gas that's still holding the N2H+, which allows this correlation to stay. So we do not expect this to stay the same at if you increase the resolution of the observations, which you could potentially do with ALMA. Looking at the ratio of these two integrated intensities with 1.1 millimeter flux, if you see a correlation in there, please let me know because I see absolutely nothing. They stay pretty constant. So the next thing we want to look at is our velocities versus galactic longitude. And so this is the CO map from Dame et al. In 2001 that just shows the velocities of the CO clouds that they observed. Well, our data fits right on top of it. I can blink them back and forth a little bit, but basically wherever the CO is the brightest, that's where our data points line up, which does make some sense because we are looking at areas where the gas is collapsing, so the CO should be, there should be a lot of CO there as well. So with just a basic velocity, you can compute a galactocentric distance, which does not have an ambiguity in it, and you can see our histogram of sources versus galactocentric radius, and you can see the features of the Milky Way itself with the molecular ring, Sagittarius arm, our local arm, and then the outer galaxy and Perseus arm. Now looking at some of the source properties along galactocentric radius, we can see our line width versus distance from the center of the galaxy, and it does change some, but that's less than 1 kilometer per second, and our channel width for our observations is greater than 1 kilometer per second. So this is probably not a significant change. We also do not have a complete set of data out in the outer galaxy. Looking at the integrated intensity of HCO+, there's no change, and we also see very little change in 1.1 millimeter flux. Now, the next step would be to say, okay, well, now that we have a galactocentric distance, well, let's turn that into an actual distance from the sun and see if we can make a map of our galaxy. And so we can do that by basically plotting or finding both distances near and far for every single source, which would be shown in the blue circles and the red squares. But for some of those sources, we might be able to break that ambiguity and that degeneracy. And so for that, we have the green triangles. Now, what goes into a green triangle where we've resolved the distance ambiguity would be sources, BGPS sources that were well matched with the Pareto and Fuller IRDC ellipses. So if we were within that IRDC ellipse, we considered it a source. From that, we then did a by eye comparison to say, do we believe that these things are actually associated by comparing the BGPS image with the MIPS and 8-micron images. So that added, I think, is about 400 sources. We also then, any source that was in the outer galaxy, of course, does not have the ambiguity. Sources that lie at the tangent distance do not have that ambiguity, as well as sources that have forbidden velocities. So these sources out here correspond to velocities that are not allowed in the rotation curve under here and correspond to the outer arc. So using kinematics, matching with known distances and known regions, we were capable of taking our 1900 sources and finding actual distances to about 650 of them. And we had about 1,400 detections, so this makes it almost half of our sources. And this is a conservative estimate of how many that we actually could do. But looking at the properties of these, the average distance to these sources is about 2.5 kiloparsecs with a median size of about 0.75 parsecs. So we're not looking at cores in this sample. We are very much looking at clumps, so there's multiple cores inside of them. One of the interesting results that we found was our size-length relationship. The Larson relationship is plotted here in black that goes through our data points. While it does go through our data points very well, it goes right through the center of them, the correlation between them, I could draw a number of lines with different slopes that would equally fit that distribution. And this has also been seen in CS in these things where the size-length relationship sort of breaks